Hello and welcome to Lecture 62 of my class From Data to Decisions. I'm Chris Mack, your instructor, and here we're going to talk about building models. We're actually going to review many of the aspects of how to build a model that we've touched on almost incidentally in the past many lectures. But we'll try to formalize some of these ideas, some of these concepts, and add a few more details to the prospect of building models. So what is model building? First of all, we have a general process, a general procedure we go through trying to build a model. It begins with experimental design. I'm assuming we're actually going to run an experiment, collect data, and use that data to build a model. Sometimes, of course, we do observational studies and the data is already in existence and we don't have much choice as to what data is there. Let's assume that we're doing the more traditional experiment data collection model building exercise. Begins with experimental design. We're going to talk about the design of experiments in a coming lecture very soon, actually. So we'll get more into the details of that. We collect our data. Then we begin the process of building a model. It's an iterative process. Sometimes we know almost exactly what kind of model we want. We're just going to test it and make sure it works. But often we're in a more of an exploratory mode and we're not quite sure what are the right terms to include in our model. So we're going to build a model and refine it over time. Then we're going to validate this model after we're done building it. Now, this linear step, one step after the other that I've described here, very frequently breaks down. It's not exactly quite so linear and self-contained in each step. Often we iterate. Design an experiment, we collect some data, we start to build a model, and we realize we've got multicollinearity that we need to break by collecting data in a different regime. Or we see that the terms of the model require more data than we thought we needed in order to get small confidence intervals around our parameters, or something else. So we often have to iterate and change the experimental design or collect more data. We generally want as much data as we can possibly get. The more data, the better. But if we have p parameters in our model, we typically want 10 times p data points, 10 times as many data points as we have parameters. We don't this is not a rule that says you have to have it, but think of that as a guideline when you're designing your experiment. If you have a model in mind, this is the kind of numbers of data points that we hope to be able to get. And finally, although it's very dependent on your specific application, the best way to build a model almost always is to have some underlying theory that guides what you're doing. Sometimes we're in a very data exploratory mode and we just really don't know what's going on. So we'll do scattershot collecting data and see what comes out. But that's not usually the case. Usually we have some theory in mind. We design the experiment in order to look specifically at how things might behave with respect to that theory. So we use that theory not only in the experimental design, but in the model building itself. Let's talk about one of the approaches that is common in a more exploratory data analysis mode called automated model search. We will sometimes use this even if we're not in an exploratory mode, but this is usually an approach we use when we've got a bunch of parameters and we're not really sure which parameters, which model terms are needed. So I've got several predicted variables. Maybe I have linear terms or higher order terms. Maybe I have interaction terms. Maybe I have more complex functions of these variables. And maybe some of these predicted variables are in fact unneeded. So how do I build a model? We can use an automated search in order to be more efficient about how we build our models. One of those options is something we've already done in this class, full search. You run all model subsets. In a previous lecture, we looked at subset regression and how we compare a subset model to a full model. So in a full search, if we have k parameters, including the intercept, then there's going to be 2 to the k minus 1 subsets. Well, that grows pretty quickly, as you sure know. If I had, let's see, 8 parameters, 7 that aren't the intercept. So 2 to the 7 is 128 subset models. Well, of course, when you add higher order terms and interaction terms, you might only have a couple of variables, predictor variables, that with higher order terms and interaction terms can easily produce something like 7 or 8 or 9 or 10 parameters, and then the number of subset models can get quite large. If the number of subset models gets large enough to where a full search is not practical, then we can use something called a forward stepwise regression or a backward stepwise regression. I'll go through the forward stepwise regression in some detail in the next couple of slides. The backward stepwise regression is pretty much the same thing operating in reverse. In the forward stepwise, we start with just the intercept, and then we start adding variables one at a time to see if it makes sense to keep that variable model. In the backward stepwise regression, we start with the full model. We've got everything possible in that model, and then we say, which term should I remove? I find the backward stepwise regression more intuitive, but both of these work. And sometimes you might do both and see if they converge to the same model. Full search is the best when you have that opportunity. The number of parameters is not too great, and usually something like 10 or 11 is when it starts getting cumbersome to do full searches. And we've already talked about this and looked, in fact, at this slide in a previous lecture, so I won't go through it again. Recall, though, that there are a number of possible metrics to judge how good your model is doing. Mallow's CP, for example, judging subset models. The AIC or the BIC, sometimes called the SBC, the Bayesian information criterion, are probably the more popular two to use. Adjusted R-squared is sometimes used as well. Let's go through in a little bit more detail the forward stepwise regression approach, because if you have too many parameters for a full exhaustive search, you might want to use this approach. So how does it work? Well, we start by writing down the full possible model, so you know the maximum number of parameters that you could possibly have. It includes functions of the predictive variables, interaction terms, everything that you might include. Suppose there's 20 of those. So now think of each one of these as its own predictor variable. So if x squared is there, think of it as just its own predictor variable. We then pick two significance levels. One, a significance level to make sense to add a variable, and another, a significance level where it makes sense to remove a variable that's not needed. You must have the significance level for the remove to be bigger than the significance level for the add in order for this algorithm to work. So here's some typical numbers that people like to use. In step one, take y, press it against each model term individually. In other words, we have a model with just two parameters, an intercept and one term. We get a coefficient for that one term, and we calculate the t-value for that one term, and a p-value associated with that t. We assume it's students t distributed, for example, depending on the type of regression. In all of our regression types, maybe even logistic or something else, we can still calculate a p-value associated with that specific coefficient. Now remember, it's a model with only two terms. But if we had 20 possible terms, we can do that exercise 20 times and look at every single two-term model out there. For all of those, we find the one model that has the smallest p-value. If that p-value is less than alpha add, criterion for adding a new term, then we add it. In other words, we look through all 20 possibilities and we pick the most significant single term that we can find and we add it to the model. Now, this is our best two-parameter model. So we now do it again. Got a two-parameter model, we're going to add a second parameter, a second variable, a third parameter. And then, so now we have maybe 19 left, right, in my example. So we go through and we want to just add one and check that three-parameter model and look at the t-value of that term. We do that with every possible combination, and we find the value with the smallest p-value for that term. And if it's less than alpha add, we add it to the model. Now we have the best two variable three-parameter model we can find. But then we have to be careful, because when we added this new term, we've affected the significance level of the previous term. So we look at all the previously added terms and see which one has the lowest t-score, and if the p-value for that one is bigger than alpha remove, then we'll remove it. Right? So adding some of these new terms might render some of the other terms we already have in the model insignificant because of multicollinearity. And finally, repeat steps 2 and 3 over and over and over again. We keep adding more and more parameters if they're significant, and removing parameters if it turns out they're not significant, always by looking at the t-value and the p-value that is the most extreme. We do this until the model stops changing. The model stops changing, we stop and say, this is our best forward stepwise regression model. Now, I won't go through this level of detail with the backward stepwise regression, but it basically runs in reverse. We start with a model with every single parameter in it, look for the one with the biggest p-value, the least significant term, and we take it out. Then we look at everything that's left, and we do the same kind of thing again. Of course, these forward stepwise and backward stepwise regression techniques have been encoded in software packages like R, so those routines are available in an automated way. You don't have to figure out all the details of implementing this yourself. One of the things I'd like to mention about this process is something called omitted variable bias. Now, we're trying to find every regressor that needs to be in our model and trying to exclude every regressor that shouldn't be in our model. But if a correct regressor is missing from the model, it has a very interesting effect. It biases the remaining parameters in the model. Why? Well, often the missing regressor is correlated with the regressors that you actually have in the model. If that's the case, then keeping this parameter out will end up changing the values of the coefficients of the regressors that we've kept in. That's called omitted variable bias. It's biasing or changing the parameters depending on whether we include or not include that regressor. Now that assumes that we have some multicollinearity present, which is almost always the case. But if xk, the missing regressor, is orthogonal to the other variables, then there will be no omitted variable bias. That would be fabulous. That's what we always hope for. We love having orthogonal variables in our model. If that's not the case, generally it's not, then omitted variable bias will exist, and we have to keep that in mind. And that's why we want to make sure that every correct regressor is actually included in our models. One last topic on model building through these full searches or forward stepwise, backward stepwise regression techniques is that we are testing a lot of regressor terms, not all of which we keep. We know that the number of degrees of freedom in our final model is going to be n minus p, the number of data points minus the number of parameters in the model. But hidden in the model building process is the fact that we've tested lots of regressors that we decided to leave out. Well, in fact, every time we test a regressor and then decide not to include it in our model, then that is a hidden or uncounted degree of freedom. We've used information about the data set to decide to exclude that particular model term. Therefore, the total number of degrees of freedom in reality is both the counted and the uncounted number of parameters. Well, sometimes we search through a large number of parameters to decide which ones to keep, and so the true number of degrees of freedom sometimes can be quite a bit smaller than we think. Now, if when we're all done, I give you my final model, you have no clue whatsoever how many different models I went through to try to find this one. You have no clue about all the regressor variables that I decided not to include, right? The x squared and the x cubed and the x to the fourth, the interaction between x1 and x2 and x1 and x3, et cetera, et cetera. There might have been a dozen, 20, 50 different regressors that I've decided not to include in the model by looking at them and determining that they're insignificant. That could seriously reduce the number of true degrees of freedom in the model. Once the number of true degrees of freedom in the model starts becoming close to the number of data points, we can get to a situation where we're really just fitting the noise. We don't have enough degrees of freedom to justify our faith in this model. And yet you can't really tell if in the end, all I show you the final model, I don't tell you anything about regressors that I tested and left out. We sometimes call this trolling for effects. And if in model exploratory way, we look through lots of effects and have a fairly limited number of data points, you look through enough models, you'll find a model that's significant just by random chance. So always be careful and always think about the uncounted degrees of freedom. Model validation. One way to catch those kinds of problems where it looks like you have a significant model, but really you're fitting noise and you don't realize it. One way to catch that is through the process of model validation. Just because a model can fit a data set, because we have forced it to, we've found the parameters that give the best fit to that data set, does not mean that we have a model which is good at making predictions. Sometimes we do, sometimes we don't. So we use a process called model validation to help us in understanding whether a model is good at making predictions. And often that's, of course, our goal, is to have a model that can make predictions. So how do we validate our model? There's really three validation approaches, and it's great if you can use all three. Depends on the circumstances. One is maybe the basic thing, the idea of science, which is we want the learning we get from this model to cohere with what we already know. All right, let me try to give you a concrete example. Suppose I'm building a model for how the anneal temperature of a specific class of polymers affects the solubility of that polymer in particular solvents. So I want to be able to predict how anneal temperature and maybe some other parameters affect the solubility of that polymer in solvents. Well, maybe I have quite a bit of knowledge already. Many people have studied this. There's several different theories for polymer solubility in solvents, and we have some basic ideas of how things should behave. Now I collect data and I generate a model. Does the model cohere with existing knowledge base science, or is it opposed to it? If it coheres, that's a bit of a validation that our model is working. If it's opposed to what we've known in the past, well, maybe we've made a discovery. Maybe we've learned something new. It could be very exciting. Maybe we're fitting the noise. We have to be very careful. If the model doesn't cohere to our existing knowledge base in science, we should be skeptical and require even further validation before we believe that we've actually discovered something new. So that's kind of a baseline idea in science that we always try to apply. Outside of that, there are a couple of statistical techniques for validating our models. First, compare the model to new data. So we generate data, we fit a model to that data. Now we've got a model. Well, collect some new data. Does the model match that new data well? We'll talk about that in a moment, and we'll also talk about the idea of data splitting. Randomly split our existing data into two pieces, a calibration piece, or a training sample, and then a second group to validate. We call it a holdout sample or a test sample. Let's talk about both of those in some more detail. First of all, comparing the model to new data. We've regressed the model to our existing data. We've gotten best parameters. Now we'll compare the model, we'll regress the model to the new data, and we'll get a new set of parameters. How much have those parameters changed? How much do the coefficients change from one data set to a second data set? Well, we can use what's called a two-sample pooled t-test for each of the coefficients. Ask ourselves, null hypothesis is that the parameters haven't changed. They're in fact the same parameter in both data sets. But we'll do this statistical test to find out if, in fact, the parameters have changed within their confidence limits. And in that way, we can assess the predictive power of a model. Probably the more popular way of doing it, though, is to compare existing models' predictions to the new data. Of course, a lot of this depends on what we care about. Do we care about making predictions, or do we care about interpreting the meaning of the model coefficients? If we care about making predictions, we'll compare the predictions of the model to the new data, look at the difference, the residuals, what we call the predicted residuals, and find the mean squared predicted residuals. We will then compare the mean squared predicted residuals to the mean square error that we got when we did our regression. And so we did our regression, we have a mean square error of the residuals from that calibration step, that training step, and we compare the two. And we want to know, is the model valid? If the MSPR, the mean square predicted residuals, is small enough, typically less than a factor of 2 larger than the MSE, then we say it's done a good job of predicting. The next thing we can try is data splitting. This is especially useful if we have large data sets. If we have a fairly large data set that we can use to calibrate our model, why not split the data up into two pieces, a training piece and a validation piece? Typically take maybe between 50 and 80% of the data and use it for training or calibration of the model. And we'll use the remaining piece for validation. It's very important that we split the data randomly. For example, we might break the data into 5 parts. We'll take one of those parts, 20% of the data, as a validation, 80% of the data for calibration. Well, in fact, if we have these 5 parts, we can do that exercise 5 times. Right? We have 5 different potential validation data sets. So not only can we look at the validation results for one of those splits, but of course we can do it 5 times. That's called 5-fold cross-validation. And in general, we can split it up into K parts, whatever K you decide to pick, and then you have K-fold cross-validation. But because we picked these parts randomly, we can in fact repeat this many times, right, with many different random splits, and get, in fact, a lot of good statistics on how good your model predicts these random splits or pieces. Keep in mind, however, the optimism principle. The validation data set is always going to have a worse MSPR than the training MSE. and we're going to look for how much worse they are. All right, let's review what we have learned in this lecture. As always, you should be able to quickly and easily answer these questions. If not, please go back and review the material. What are the 3 automated model search approaches? Explain what an omitted variable bias means. How can model building result in uncounted degrees of freedom? And finally, what are the 3 model validation approaches? Well, as I said, we've actually talked a lot about model building over the course of this course because we've built some models already. But here we've tried to systematize the model building process. There are other pieces to the model building process, however, and some of those pieces include design of experiments, and that's coming up very soon. Till then.